So challenge number 3 was a really interesting problem, and I couldn't fit all of it onto this sheet, so I put it on a lot of separate sheets and then attached them all as PDFs. So to start off, basically what the problem was laying out was it was asking you to derive an expression for the electric field strength at a point Z directly above the center line of an infinitely long strip of charge. They called it a sheet of charge. So this diagram basically represents the sheet of charge, and in the y direction goes to positive and negative infinity, and there's ends here, but just imagine it goes on this way to infinity and on this way to infinity. And in the x direction, you can see here, it goes from L over 2 to negative L over 2. So those have bounds, but in the y direction it has no bounds. So what we start off doing is something that we discussed a little bit in class actually. You choose an arbitrary point here, Q, and it has width dx and length dy. So we have Q was just any point on the strip, and again we did this in class, and it was good to choose a point that was just some random point on the strip relatively close to Z. So we know that charge density is the charge divided by the area. Actually, it's written right here. Charge divided by the area, or eta, which is what we use, is charge divided by area times dy dx, which basically means it's the charge density multiplied by dy, which is the change going this way, and dx, which is the change going that way. So eta basically represents in this situation, or eta dy dx basically represents in this situation the charge density as it moves, of this little area Q, as it sweeps out dy and dx. So we use the term eta dy dx to represent the charge density. So down here we have to find this length r between our arbitrarily chosen point and the point Z. So we can make a triangle that's actually a right triangle that has side length, well, I'll get to that in a second, but it's the square root of x squared plus y squared. And then you have, this is given in the problem, it's just side length Z, and we're trying to find this r. So, and you have angle theta here. And it's actually, I think it's easier if we rewrite this triangle in 2 dimensions so you can view it more clearly. We have Z here, r here, which is what we're trying to find, and you use the Pythagorean theorem to find the square root. It's just the square root of x squared plus y squared, and we don't have those values, so we have to keep it in the form x squared plus y squared. And the way that we find r is that you have, again, use the Pythagorean theorem. You have the square root of z squared plus this side, which is x squared plus root x squared plus y squared. But because it's this is kind of confusing, because it's z squared plus x squared plus y squared squared, and it's the square root. These cancel, and what you end up with eventually is r equals the square root of x squared plus y squared plus z squared. So this is your side length r. Okay, so then you have sine of theta, and this is this angle here, which is necessary in order to continue. So you have z over the square root of x squared plus y squared plus z squared, because that is this side length here, and sine is obviously opposite over hypotenuse. So we have opposite z over hypotenuse. And then moving on, right? Yes, because the 2 points, excuse me, because the point that you're trying to find Z lies directly above the very center of the strip, the very center of the line. Every point on the left and the right of that center point Z are going to cancel in every direction except for straight upwards in the Z direction. In other words, all of the electric field, the only aspect of the electric field that we care about calculating is straight up in the Z direction, because it's over the exact center of the sheet of charge, which is actually really nice because all you need to calculate is straight up, which is why we had to use sine earlier. So now we can use the equation that we know for finding a a charge, excuse me, for finding the electric field from a point charge, which is kq over r squared, yes, r squared. So this is basically, sorry, it's just a lot of writing. And kq over r squared is this charge density, or eta, and because r squared is r squared is x squared plus y squared plus z squared to the square root, that those cancel, and you just get k eta over x squared plus y squared plus z squared dx dy multiplied by z times square root x squared plus y squared plus z squared, and eventually you get k eta z dx dy. You can actually pull out the dx dy, but I didn't here. Over x squared plus y squared plus z squared multiplied by the square root x squared plus y squared plus z squared, and you know from math that this is just this value to the 3/2. Yeah. So basically, we're nearing the end of finding the expression for E. So we remember that Q is actually equal to eta, which is charge density, multiplied by dx dy, or the amount that it sweeps out in the x and y directions. So we have E is equal to kqz over x squared plus y squared plus z squared to the quantity to the 3/2. And we can rewrite it as this. So that is finding the expression, but that's just for the single point. So we still need to figure out what it is for the entire strip. And next you use integration in the y direction at first, and then in the x direction, or in the x direction first, and then in the y direction, to sweep out the area of the entire. Yes. Okay. So that's what we do now. So okay. So yes. So the y in the sheet extends infinitely in the y direction. You can remember from the first part, negative infinity to positive infinity. In the x direction, it only goes from negative L over 2 to L over 2. So first we integrate with respect to y and find basically the charge of that infinitely long but infinitesimally small thin strip in the y direction. I'm sorry. Okay. So then what you do is you integrate from negative infinity to positive infinity k theta or eta z divided by x squared plus y squared plus z squared 3 over 2 dy equals this value. So I didn't actually do that integration, I just put it into Wolfram alpha, but once you have this value, then you just integrate again, because you use a double integration because you're not trying to find one change. It's two change. It's you want to find the area from negative infinity to positive infinity in the y direction, but then in the x direction you also want it to sweep out area from negative L over 2 to L over 2. So in order to do that, you have to use a second integral, and basically you just plug in the result of the first integral into the second, and then again I just use Wolfram alpha. But the result of that was 2k z eta multiplied by tan inverse of x over z divided by z, and you can just kind of pull out the 2k z eta because that's basically just a constant, and what you're left with is tan inverse of x over 2 divided by z. No, excuse me, z divided, yeah. So z, I can't read my handwriting. Divided by z, and with the bounds of L over 2 to negative L over 2. That's its upper and lower limits, because that's what you're integrating with respect to. So then we can rewrite this briefly as we know that k obviously is 1 over 4 pi epsilon naught, and then we can employ that knowledge to rewrite this as 4, and then it's just 1 4 pi epsilon naught. The 4's cancel eta, so you get eta pi over pi epsilon naught tan inverse of L over 2z, and that's the answer. That's the expression that you use in order to calculate the electric field at a distance z away from the center line of an infinitely long sheet of charged sheet. And then there's a last part which asks if Z is much smaller or much larger than L, does it still hold? Is it still a valid expression? And it does, and you can prove that because, well, actually, just conceptually, if you think about it, if Z is much smaller than L, then it would be, I get to it down here, but it would be basically like an infinitely long sheet of charge in both the x and the y directions. It would be like the electric field strength of a sheet of charge, because you're so close to it that it's no longer a strip from L/2 to negative L/2. It looks basically, it's like a sheet of charge, and it was actually really neat. It was really cool, because what came out was that it actually was the exact same expression that you use to calculate the electric field of a sheet of charge, and it was cool. So, but basically, the expression that you have here, eta over pi epsilon naught times tan inverse of L over 2z. This is the only part that deals with L and Z. So if you have L as a really, well, what's the other way is, if L was if Z was a really large number and L was relatively small, then this L over 2z would subsequently be a really small number. And you can remember from math, it says right here, remember from mathematics that the tan inverse of a really small number is a really small number. It's the exact same number that you entered in. So in the case of Z, L over 2z being really small and Z being a really large value, it would be the exact same. It would be the exact same answer. So E would be equal to eta over pi epsilon naught times tan inverse of L over 2z, and that gives you the same answer. So that proves that if Z is really long, then it's true. But like I mentioned it before, it was actually really cool to figure this out. When L is a lot larger than Z, the expression will approach, if you graph it, actually, you make a graph of the tangent function, the upper limit of the tangent at pi over 2, no, not the upper limit, but it's kind of it's asymptotic to pi over 2. It goes up and up and up and up and up to infinity. So when you plug in something really large to tan inverse of tan inverse of something really large like infinity, okay, let's use the example of infinity. Tan inverse of infinity is pi over 2, because, or exactly pi over 2, because it's asymptotic at pi over 2 to infinity. So when you have L being really large comparative to Z, it looks like infinity, and when you plug it in, it's basically you just get pi over 2. So what you end up with is eta over pi epsilon naught times pi over 2. The pi's cancel, and you get eta 2 epsilon naught, which is the exact same expression that you use when you're trying to calculate a field of charge, not a strip, but a field. And it makes sense. It makes perfect sense, and it's really cool. So, and that's how you prove that. Okay, that's it.